Take your seats and we'll get moving. All right. So on to our second session, and didn't want to spend too much time on the intros because I think, as I said before, you want to get into the content as soon as possible. So we're going to hear from Jonathan Krebschet, who's come from EMSI, senior developer there, and the topic of the day is templates in the wild. Take it away.
Thank you very much. Well, good morning, everybody. I seem to be a little bit louder. That's a problem with deep voices. Anyway, I'm Jonathan Krebschet. I'm a senior infrastructure developer at EMSI. So what exactly does that mean? We are, oh, by the way, EMSI is Economic Modeling Specialists International. We just call it EMSI for short. Most places that you see it online, it's EMSI, so we just always stick with that. So who am I? Well, I develop and support the basic infrastructure of EMSI's data department's infrastructure, both hardware and software. I've produced over the years economic models for the US and UK and Canada, helped push D into usage at EMSI, and I've been developing with D since version 1. The first time that I was introduced to it, my dad sent me an instant message and saying, "Hey, saw this on Slashdot. Looks like a language that you might find interesting." And basically, my first reaction was, "The language I've been looking for! High speed, and I can do everything I want, and it's not C++. Made me very happy. So what is EMSI? We're a software and data company that specializes in labor market data and economics. We started in Moscow, Idaho around 2000. For those of you who don't know, Moscow, Idaho is this little tiny college town. We have the University of Idaho in it. And about 10 miles away, we have the, Washington State University. So we're up in the north of Idaho. We were recently purchased by CareerBuilder. I don't know if any of you have ever heard of them, but they're a company out of Chicago. We have roughly about 100 employees in the US and Canada. By the way, I checked, and roughly 8 to 9 employees currently using D just about every day. So it's a small number of us who are using it, but compared to the size of the department, that's basically the entire department. So we're doing well there. Major clients include education and workforce professionals. So these include colleges, universities, workforce investment boards, economic development councils, private organizations, and basically anyone who's interested in labor market data for their given region, wherever they are working. So what is labor market data? Well, labor market data forms the basis for understanding the connection between people, economies, and work. So things that you might measure with labor market data might be job counts, occupational wages, industry output, population demographics, and many more. People use this data to better understand regional workforce trends and make more informed decisions about workforce investment and development within their region. So basically, data equals intelligence and being able to do things smarter. So what kind of data do we produce at EMSI? Well, we produce jobs, earnings, sales, value added, which many of you probably would recognize as gross domestic product, but we produce it at much more regional levels. And then population counts for roughly 1,100 different detailed industries. So top-level industries would be like your agriculture industry, your transportation industry, and then detailed situation examples would be something like air transportation or something of that sort. We have roughly 750 occupations that we cover, like CEOs, farmers, and other occupations. 16 demographic groups are covered in our data. We have in the areas of roughly 3,100 different counties, 40,000 zip codes in the US, 51 states, that includes the District of Columbia. And then we cover years between 2001 and 2024. and that's just for the US. All of this together for just the US is roughly about 13 billion data points of data that we produce each quarter every single year. And so we have this quarterly data run. But in addition to all of this, we also produce data for the US, UK, Canada, Brazil, France, and Australia. So we're keeping up on lots of countries, and then we're adding to this every year. So this has required increasingly complex frameworks that we've used over the years and languages to handle the data, but it wasn't always that case. So what was it in the beginning? Well, in the beginning, there was Excel and VBA. Fantastic language, as we all heard just at the last talk. And this worked great. We had a laptop that was doing all of our data processing that had to be sitting on two 2x4s with a fan blowing behind it because we didn't want it to overheat and have the computer shut down in the middle of data processing. This is also back in the day when we didn't do any logging, so if it died, we had to restart from scratch. Always exciting. Eventually, we got sophisticated and started using MySQL as a storage engine, and then eventually we started using MySQL to do the computations, because the majority of our work is set-based. And then we continued to use Visual Basic and Excel to handle all of the structure of running all the different queries. Eventually, we then transferred some of the architecture that we had to running in Bash. And as many of you, that is not the best language for handling running of large data processes. And so surprisingly enough, we then went to PHP and still continued to use MySQL. This has actually worked really well for us. Even though PHP is not the best language in the world, it was a language that everybody in the company knew, and so we were able to just integrate directly into it and develop quickly. But up until recently, our structures were very ad hoc, and we started to realize that we needed some common concrete structures for processing data. And that led us to D. So, why D? Well, we had three main goals for a data framework that we wanted to create. And that was something that really was core to our understanding. First off, we needed to improve our developer productivity. We needed higher level building blocks. We needed more generic solutions for better reuse, just so that our data developers could go in there and very quickly hash out what do they want to do, write the code for it, and have it just work. But not just work. We also needed it to have increased data quality guarantees, such things as strong typing, testing, more compile time and runtime checks. Just some very basic things that you take for granted in D, but because we were using SQL and PHP, it wasn't quite as possible. And last but not least, we wanted to improve our processing efficiency. We've been moving to more and larger data sets, and we just needed it to use less memory, be running at native speeds, and not be limited by database. Up to this point, we would run single queries, and everything would be single-threaded. And even though we would have this huge MySQL database server, it just would take too much time, and we weren't able to run anything concurrently. So what was it that D actually allowed us to do? Well, it allowed us, the thing that we liked so much about it was that it gave us it was accessible to developers with a wide range of skills. So we have developers in our department who are just now learning to program, but they've got an economics background. So we're starting them on D, and they're finding that it's actually really quite easy. And thanks to you, they're actually learning quite easily. We really loved the feature set. One of the things that I really like is that there's inline assembly directly in the code. It's not something that is a second-hand idea that was just thrown into the language, but it really is part of it. And we've used it to significantly improve some of our processes. But at the same time, we have associative arrays in the language, which has made it so that we can very easily have a new user say, oh, I need to do X. Well, great. Here's an associative array. Go use that. Works just well enough. We found that it had very powerful templating capabilities, which allowed us to optimize a lot of our specific use cases. And that was just one of the great things. Had easy C function calling. This was extremely important because when I was first starting to work with D, I needed to be able to call, if any of you have heard of BLAS functions, or BLAS functions for linear algebra calculations. I needed very high-speed calculations of linear functions, and being able to call C functions was just the thing that I needed. We needed fast compile times for turnaround speed of development times, and it was great. It did exactly what we needed. But last but not least, it had built-in unit testing, and that was one of the greatest strengths that we could have, because then we could ensure that what we were developing was exactly what we planned on it executing as. So let's take a look at a couple of data structures that we figured out that we really needed when we were working on this framework, now that we had picked D as the great language that we were going to use. So what were they? Well, we had 4 of them. We had hierarchies, dimensions, stores, and cubes. So what does hierarchies look like? Well, hierarchy embodies a parent-child relationship, something like this. And every child can only have one parent, and only one parent. There is only one root, and they're connected in such a way. So an example of a hierarchy like this would be, the root would be the US nation. And then underneath that, the first set of children would be the states. Next step underneath that would be counties in the US. And the last step would be zip codes. And this is something we work constantly with hierarchical data, and this is very important to us. So what is a hierarchy defined as? It is a connected, directed acyclic graph, for those of you who might be interested in that kind of a thing. Next, we have dimensions. Dimensions aren't arrays. They're abstract containers for hierarchies. So an example would be, we would talk about a dimension being area. And then the hierarchy would be talking about the nations, the state, and the counties inside of it. It has templated names that become part of the type. This was very important for us. And they're used for filtering, grouping, and labeling. This has actually been very, very important and very useful, and allowed us to have some very high-speed optimizations included in it. Next, we have cubes and stores. Cubes contain stores that are holding all the data, and they offer common functionality for all the different storage engines that we have in the back end. The stores combine dimensions to create address spaces, and these address spaces aren't memory address spaces. They're basically points in a space defined by the hierarchies. And they store measures. Measures would be, as an example, jobs or earnings. That's what we define them as. Essentially, measures are the same thing as data. So what does it look like? So as you can see here, we've got our cube encapsulating our storage. The storage encapsulates multiple dimensions with hierarchies inside of it. And then we have lots of measures stored in the storage. One of the things that we use here is we use a number of alias this in place. So the dimensions have an alias this to their hierarchy, and the cubes have an alias this to the storage. So these are the basic building blocks of our data framework. Let me show you now some of the code, how they look in code. So here's their prototypes. We've got a struct, that's a hierarchy defined with code T. A struct, that's our dimensions with a specific name associated with them and their node type. We've got data stores, which we've converted to classes. Originally, we started off with structs, but we ended up converting them to classes because they were better as a reference type. And they are holding all the data, so it seemed more appropriate to be passing them around that way. Otherwise, we had ref placed all over our entire code base, and then we would forget it, and things would slow down a little bit. One of the things that we also really liked here is that is the template constraints and being able to just place those on there and ensure that what we're doing, again, is what we expect it to be. And last but not least, we have a cube that takes a storage type. So what have we developed so far in creating this? Well, other than the struct here, this is an example of how we might use it. We have our node measures. So here's employment and earnings. And then we've got our cube wrapping around our data store with our measures. And then we've got dimensions such as area and industry. And then we can use a function for creating this type for us easily. So we call it dense cube, and we pass in our measure type. And then we have our area and our 2 dimensions defined there. So for us, it's a very simple set of calls, and it's easily definable. So what we created so far is a data framework that is a library of templated structs, classes, and functions. It's roughly 10,000 lines of code, and it's used for mathematical operations, dimension manipulation, cube serialization, data optimizations, testing, and many other functions that we also include into this library. And this is getting used heavily every day, and with fun turnaround of, hey, here's another bug. OK, we'll fix that, get that turned around, add some more unit testing in. It's been very useful to us. So in the next few slides, we'll get to see 5 examples of techniques that we use and employ in our framework. So first off, let's talk about the data store basics. This is a dense data store. In dense data stores, we store all of the structs in a contiguous array. And we're able to, because the dimensions have known lengths, we're able to define the array at runtime once and not have to resize it. This has actually been something that allowed us to run some much faster code because we have known quantities. Here, we define an address as equal to a static map of applying getType to dimension. So what we're doing is we're going in, we're yanking out that specific type out of the dimension using a very simple template. And again, one of those great things that we've found in D is these very simple templates. And they are so powerful, and then combining them together, we've been able to do some very powerful things. But in this situation, it's just something very simple. We're just creating this address type, which is a tuple of whatever the dimensions define. We can then create a variable called root address and define it as immutable because it will never change. And then we pass in these dimensions, and then it gets set there. One thing that we have noticed was we needed to keep the mutability of many of the dimensions. This came up when we converted this entire library to being const and immutable compatible. Took a fair amount of work. Thankfully, in the latest release, we were able to get over the last few hurdles. But it really has benefited all of our code to have that. And surprisingly enough, there aren't that many unsafe casts, but they do exist in the code. But here, we did need to pass in our dimensions, and we needed them not only to be defined in the type of the data store, but we also needed to define them in the constructor because we needed to grab that mutability. And this was the best way that we could find to do that. Later on in the code, we do store the dimensions, and we store them all as immutable. So if we pass them in as immutable, we want to make sure that they don't have to be recreated or copied or duplicated, and that's why we pass them in through the constructor. The op index in the past, because we're using PHP and SQL, we never are able to truly define what types we are able to work with. But in here, because we can template the entire structure, we're able to then define the op index with a specific number of parameters through the address tuple. And this has made our life a lot easier. It's certainly increased our error checking, because no longer will we say something like, oh, hey, we're going to use LATA as our string and industrial construction. No, it's going to tell us, no, you're not allowed to do that. We're talking in this situation about areas and industries, and those two are defined by integers. And then we also check to make sure that those integers that you're passing in are part of the hierarchies. So we don't allow for arbitrary creation of new points in the address space. And this is just yet another level of checking that we are using. So moving on. Dense cube addition. Let's see, it's not quite catching up. Here, just a second. Give me a second. There we go. So with dense cube addition, we run into a number of different situations where we need to have a couple of different cubes. Let's say left cube here, and we need to add it to a right cube. Well, this is something that we do really need, and we eventually come up with a new cube. Here we are adding the measures. We don't add dimensions or anything of that sort, and it allows us to check both the hierarchies and the dimensions, make sure that everything is as expected. A little bit of lag. So what does this look like? Here's our dense add function, pass in our left cube and our right cube. Thankfully, we can now define them as constant. Check to make sure that they are cubes. And in this assertion, we can make sure that the dimensions are exactly the same. This is not something that you would find in a whole lot of other libraries. In fact, most of the guys in my department have never seen this kind of capability to go in and say, no, these cubes are truly the same. And yes, you can add them together with known quantities, and they will work. So next, we have an alias t, which is equal to a template that goes in and pulls out of these specific measures that are stored in these cubes, and it figures out, well, what is the integral type that you're working with? Many of the situations where we're doing this add, we have structs with multiple doubles stored inside of it. So here, it would pull out, okay, that type that you're working with is a double. And this is very important to us because, as many of you know, a struct stores all of its fields right next to each other. And if you have an array of structs that are just created as doubles, basically, you would then have, say you have an array of 2 structs with 2 doubles in them each, you have an array of 4 doubles. It's the same thing. We use this to make our code a bit faster using array operations. And something that I found was that if we do cast this array of structs to an array of doubles, I don't know who created the magic to make this work, but it realizes that the number of elements in that array is its length times the number of elements in that struct. In doing so, we can then use the array operations in D that on the back end are run through SIMD and SSE to make this code move much faster. Sadly, at the moment, the majority of these array operations are only been developed for x86 32-bit. My father very kindly went in. He's an older guy who loves assembly, and he developed for us, for the fun of it, all of the 64-bit computations for doubles. At some point, hopefully, I can get him to push that into D runtime. I've been trying to push for the last year, but he's been really busy, so he hasn't gotten around to it. Yeah, exactly. He's mostly retired. So not only does this function operate with high efficiency using these array operations, but its checking of the dimensions allows our developers to catch errors quickly and easily. This is very, very important to us to catch all of these errors, because there are a lot of people in government and private businesses who really care about our data, and because they're using it to allocate large amounts of money in many situations. And the more error checking we have, the more confidence we have in our data. And this is just one of the great things. So something else that we really use is an ability to go in and yank out what are the measures that are encompassed in these structs that we're working with, and then be able to write generic algorithms on the back end that make sure that it goes through and just works on the measures. We also have things that we define in these structs called meta measures, which modify or explain potential limits on the measures. An example of that would be mins, maxes, confidence intervals. Those kinds of things we need to be able to define in there, but we usually don't want to work with them directly. They're more of the kind of thing that you set once and then you kind of leave them alone. So we developed this template called getMeasures, which applies the isMeasure template to all the member names, a special template that we've created in our code, and it will operate on the data T that we're working with. And this can be a struct with any number of fields defined in it. One of the things that we absolutely love is that the isMeasure template can operate with CTFE and very seamlessly and easily work with all of these different measures. And no matter how our developers define them, because we're using the to lower and the ends with, we can capture whatever they're running into. So what does this look like? So we've got a variable called ret, and then we just want to for each over each of the measures and set them to 0. It's been very, very clean, very easy, and all of our developers have just found this to be a fantastic ability. My boss and I were working on a project, and he said, is there some way that we can just generically say, work on all the measures? And I said, yes. I'll be right back. I'll go figure it out. Came up with this, and it didn't take me very long because it's so simple. And we use this in a number of places, not only on the back-end framework, but also for the developers themselves. So this really has been a strong point, this ability to combine templates, compile time, function execution, and foraging over tuples to allow us to write powerful yet readable code that works with whatever measures we throw at it. And in many times, we can go anywhere from 1 measure all the way up to 10 or more. This next example is an n-dimensional tree traversal. We use a specialized tree known as a left child right sibling tree, but it becomes multi-dimensional. So we create these pointers to itself. It looks like a singly linked list, and basically it's a singly linked list to the first child, and then each child has a connection to its sibling. This allows us to have very quick access to any dimensional angle that we might be looking at to both children and a parent. So then we can do comparisons of, hey, what are the values or the sum of a child's measures versus the parent, and be able to do comparisons and potentially proportionally adjust them to make sure that they all add up correctly. So repeat type is a very simple template, something that we use a lot in our code. And yet again, simple and very powerful. So what does it look like to do this tree traversal? So here's our function. It's a pre-ordered traversal. It's basically a depth-first search. Thankfully, we just pass in the root node, and this will traverse through, recursively calling itself. And yet another optimization, we're not doing a call and then doing more if statements internally. We're doing them at compile time and significantly saving us a lot of extra jumping and that type of thing. So what does this look like? So here's an example. We've got two-dimensional tree. We've got a root with a value with an address of 0, 0. We've got 3 children on this side and 2 children on this side. So we've got 1, 2, and 3, and 0, A and B on the two-dimensional angles. So the parent connections are the bold arrows, and the sibling connections are the other arrows. And you can see the colors here. So the red and the orange are one-dimensional, and are the second dimension, and the blue are the first dimension. This gets really, really complex when you're looking at it from a 3, 4, or 5-dimensional tree. And one of the things that's left out of here is all of the parent connections. So every single one of these nodes has a connection back to its parent. And so it gets fairly complex. One thing that you might notice here is that it looks like a graph traversal if we're trying to traverse through this. But in this specific situation, it's basically a binary tree, but it's n-dimensional. Again, fully optimized. For those of you who might be interested, you start off at 0, 0. Then you're going to go to 0A, 0B, backtrack, go to 1, 0, 2, 0, 3, 0. Once you hit 1, 0, though, you're going to drop down to 1A and then 1B, 2, 0, 2A, 2B, 3, 0, 3A, 3B. And this is something we do an awful lot. We are constantly traversing through the data, making modifications. We might throw it through an optimization algorithm that goes through and compares parents to children, makes sure that they all add up correctly. And this is a small tree, but we usually work with things that are anywhere between 1 million and 5 million nodes on a regular basis. And high-speed computation really matters when you run into these situations. Something else that came up a lot, especially when we made the transition from having no const compatibility at all to being const and immutable compatible, was a common thread of we need to wrap a type with the mutability of a reference type. And this came up time and time again. An example of this would be you are returning a range, potentially a Voldemort range, from a function, and you need to wrap the mutability of the parent around each item that's being returned from front. That wrapping of mutability can get a little dicey, especially when you're working with ranges, because you have to keep the range mutable, but the individual elements that are being returned as immutable or const. This has led to some rather interesting workarounds in our code. But one thing that was always constant was this need to wrap the mutability. And so it's a very simple template that we use a lot. Here's an example out of the cube struct, where you need to go get the parent of some specific dimension. And here we refer to it by name, which means that our coders don't have to say, oh, which one was it that I picked? Was it the first or the second or the fifth? They can say, OK, I'm talking about industry, occupation, whatever they're talking about. And that makes their code much simpler. Then they can pass in the address. And we'll wrap the mutability of this around the data T. I don't remember who it was, and I think it's somebody in this room, showed me the trick of using the this. I don't remember who it was. Whoever it was, thank you very much. It was on the forum, and it was very, very helpful. We then have additional templates of going and figuring out which of the specific dimensions are you talking about. Get the index out, look up the address that they passed in the dimension, get an address node, and then we were able to build up an address tuple and get the parent ID of that from that dimension. And then we can index into the cube itself, pull out the specific parent, and cast it to the return type to make sure that everything looks correct. And if this is a const or a mutable cube, that we keep the values that are being returned that way. So all of this has been really a fantastic time of developing, but we have had issues over the years. Quiet you. The first one that we ran into was constant mutable ranges. The whole fact of, yes, the range needs to be mutable, but the individual elements need to be const or immutable when they're returned. And kind of doing that whole workaround, it just kind of, it took a lot of work, and it felt a little difficult to work with. But we conquered it. We've been very happy with that. We have found that required templating of constructors to get mutability has led to some amazingly large symbols for our constructors. I will show you one in a moment. One of the other things that I now realized after Andre's talk was that we have mix-ins in the constructors to capture the mutability of the individual dimensions that you pass in. And basically, that was the only way that we could come up with how to create a tuple that was immutable and that we could define as certain parts being immutable and other parts being needing to be passed to a function to become immutable. And that got a little tedious, and it's actually slowed down our compile time significantly. But it's still pretty fast. Backtraces. Especially for a lot of the new guys, backtraces have been a real pain because they only spit out where did it fail on the first call. But usually that's deep down inside of Phobos or one of our other libraries. And it would be really nice, instead of just saying, hey, it failed in this symbol with this address, it really would be helpful if it actually said, here's the file that it errored in, and here's the line that it ended on. Thankfully, Brian showed us address to, let's see, where was it? Address to line. And it made our development a bit easier, and especially for the newer guys. Tuples. Currently, named tuples, there's no way to actually get at the member names. So we've had to resort to always creating a struct rather than allowing people to use tuples, because we often at compile time need to go in and look at the names, especially as an example, the get measures template. It needs to go in and find out what exactly are you working with. And sadly, for this situation, that hasn't been able to be used. But I'm sure this is something simple, and I know eventually at some point I need to go in there and make it work myself and then submit it as a pull request. Just, again, I need to find the time. Another problem that we've run into is explaining expression tuples versus type tuples versus tuples. And for I don't know how many of you, just saying that is hard enough and not getting a tongue twister. Especially with the newer guys, when I say, oh yes, so we have this tuple called address, and then we have a variable that's an expression tuple. And they go, what? And I said, yeah, and then you got to pass this tuple. Wait, which tuple are you talking about? And I've had a lot of questions come back. What exactly are the differences, and how do they work? And thankfully, I've finally figured it out, but it's been difficult, especially for some of the newer guys, as you all are well aware. So the garbage collector. It has allowed us to significantly develop our code quickly, but when running with the really large data sets that we use, we found problems where it significantly slowed down our processing, and we have been migrating slowly but surely to using manual memory management in certain places to try and stay away from garbage collector, using standard allocators and some extra things that Brian has worked on. It's been an interesting transition. We've even started doing multi-processing instead of multi-threading because of the garbage collector getting in there, and especially its connection to associative arrays, and that the associative arrays getting slowed down, especially when you have really large data in there. There's no enhanced get opt. I was really excited when I saw this ticket pop up and people were working on it. The whole ability to use a function that'll define your basic help for all the algorithms that you work on. Because that's not been in there, I've had to develop something which is basically kind of subpar. It just doesn't have quite the capabilities that get opt would have. But it'd really be nice to have that in there eventually. And last but not least, this is something that's really kind of gotten us several times over. Anybody want to tell me what that symbol's the exact function? Yeah, you did it fast. Usually it takes me about a minute to try and track this one down. Thankfully, this is big, and so you can see it. Usually I'm dealing with it about this size on somebody's screen, and they're like, what happened? Like, yeah, it happened, all right. Yes. Well, I know that has something to do with this. If you run this through the demangler, it replies exactly with what you passed in. It completely gives up and just says, I give up, here, have it back. And I'm like, no, I didn't want it back, thank you very much. I wanted to, yes, all right. Anyway, but that's something that has come up a bunch. Whoop, you two were reading it. Yeah, yeah. And with all the other underscores in there, it's, yeah, especially with all the extra numbers in there, it's helpful. Yeah, exactly, yes. And I've gotten faster and faster with it over the years, but it's certainly been difficult. So in conclusion, overall, the library and its usage of D has been a success. The company's been really pleased with our usage of D. All the higher-ups are really, really happy with it. And we just loved using it day in and day out. It significantly improved our error checking, our processing speed, and our development speed. And those were the three things that we set out to accomplish, and it has been accomplished. And we've really been pleased with that. Thank you. Questions? Comments?
There's a mic on the other side, actually.
Yeah, I had a question back on your, there was an example function where you were wrapping the mutability, and you had in-out at the end of the function.
Yes.
And I was just wondering, because you're casting at the end to something else, why you have that in there?
What we found was that what was being returned, doing the multiple calls, we would run into issues, especially from here, that sometimes the mutability of the item being returned from op index would disappear, and we wanted to ensure that it stayed on there. Especially because in this situation, I think previously, when doing this lookup, might have been a previous compiler version, basically it wouldn't return correctly, and we needed it to return immutable or const. So the in-out allows this function to be called when the cube itself is const or immutable. and then we get the mutability off of this to try and figure out what we should be returning.
Right. The reason I asked was because that was the reason for in-out, was to try and push the mutability of the this object out to the result, and it seems like it failed here.
Yeah, it would. That's true. This might have been just one of those situations of something else had cropped up, and okay, we just want to make sure that it does work the way that we expect it to. So you might be right. This might not be exactly necessary, but I was basically coming up with a simple example. Thank you for the question.
Okay. I have noticed that you have used both some very advanced techniques, and at the same time you have mentioned that experience level of team members varies quite a lot. So what is your experience about actually like continuously teaching new people to get used to all those more advanced things? Is it really an issue, or it gets naturally, so kind of like the very process of getting closer and closer to the more advanced part?
There's two groups in our department. There's the infrastructure group, and then there's the data creation group. The data creation guys use all the high-level stuff and make it all work. And the data infrastructure guys, we've all basically just learned by bashing our head against the wall and just learning slowly but surely, reading off the forums, and then sharing between each other. Hey, what did you run into today? Oh, I ran into this where I had to change the type slightly, which required referencing a variable and then getting the address of it, and then casting that to a pointer of some other type, and then dereferencing that. It's just been sort of a more organic learning over time. So we haven't sadly run into any situations where the new guys really need to learn anything super advanced.
Yeah, we had some similar questions from the Ustream chat. A few raised eyebrows at your earlier comment that it was easy for them all to pick up, the people that were coming new to this. And I think one of the questions was, what were the sort of the three things that the newbies kind of stumbled on when they were first getting into D? You touched on some of the issues, I think, on your penultimate slide, but was there a sort of a general pattern of the things that people got conceptually stuck with early on, or?
Well, some of the people who were initially moving from PHP over to D really ran into problems understanding templates. It doesn't exist in PHP, and this whole concept of, inferred type inference for functions, and how does that work? They ran into problems with that, but eventually they picked it up. I think that was one of the biggest difficulties that they had. As long as nobody's trying to do anything that's been super complex, and we try and keep them from having to think about those complex issues. That's why we have two groups in our department. It's so that there are those of us in the infrastructure group who are happy writing assembly as necessary and pointer arithmetic and dealing with high-speed coding and figuring out what is necessary to do whatever needs to be done quickly. And then there's the other group who says, I just need to know how to code simply and easily and get this project done. So that's why in our department we have those two. And the people who are in the infrastructure group, they like doing that kind of thing. Any other questions?
Thanks. I'm not sure what I'm going to ask. So I guess this feels a little bit like the assembly language of like data processing, like you're going in there and hand tuning and doing as much as you can at compile time, and I guess with the goal of running your process as quickly as possible or using the fewest machine resources as possible. Did you look at more like general data processing frameworks, and how this would compare to those.
Yeah, the majority of the time, so we have some guys in our department who have used R for a number of things, Python, some other languages to play with, and usually we find that they're just too slow, and they use too much memory, any number of things, and often, I mean, there's one project that one of our guys is working on currently. He wrote it in R, and we have a server with 48 cores on it, and he'll max it out for a week. And we're just waiting for him to transition that over to D because we know that it'll be many times faster. And if it isn't, I can go in there and make sure that it is. So, yeah, thank you.
We have one more question from the live stream, actually, which was whether you had any plans to kind of open source some of the work you'd done or spend more time blogging about what you'd found. I mean, this has been fantastic sharing it here, I think, but do you have any more kind of plans for doing this more generally?
Potentially, yes. Some parts of the code, yes, we would love to open source. We do now have a GitHub group called Economic Modeling, which you can go find. And we're starting to open source some pieces of it. Certain pieces of it are proprietary, but things like wrap mutability, we might just add that as a pull request into Phobos because it is something that's very, very useful if you guys find that. So, but eventually we'll do some. There was a question back there, I believe.
Hello. In your measurement example,
Mm-hmm.
I recall correct that you decide which one of the members is a measurement based on the name? Why not use annotations there?
It's a good question. I went the wrong way. The reason why was initially one of our data developers thought that the annotations would be applying a little bit too much magic behind the scenes, and he wanted it to be a bit more readable. So the infrastructure group, our customers are the data creation guys, and whatever they say they like, that's what we do. And so we wanted to make sure that it was the most readable for them without adding any additional complexity to what their work was. And in the end, it actually has turned out to be very useful. We might in the future apply some annotations to help describe some of the data, but we just haven't gotten there yet.
All right, I think we're going to call it a day there. That's been a fantastic case study. Thanks very much indeed.
Thank you very much.
And we'll start the next session on the hour. So again, if you want to take a quick comfort break for 2 or 3 minutes, we'll kick back off with Chuck right then.